You are holding your hand in front of your face right now. Look at it. Those fingers, that palm, the slight tremor that proves you are alive. You trust that hand. You trust that it is solid, that it exists in a single definable moment, that when you move it, the universe responds in a way that makes sense. But here is something you were never told. That hand is lying to you. Your entire experience of movement, of speed, of what it means to travel from one place to another is built on an assumption so deeply flawed that it breaks down the moment you try to push it too far. And too far is not some impossibly distant goal. It is not a limitation you will never encounter. It is a wall built into the architecture of existence itself. You have probably heard that nothing can travel faster than light. But the real question, the one that should keep you awake at night, is not about faster. It is about reaching. Because even getting close, even crawling toward that speed, becomes exponentially, mathematically, impossibly harder with every fraction of a percent you gain. Why? What is the universe hiding at 99.99% the speed of light? And why does reality itself seem to conspire against anything with mass ever reaching it? Let us start with what you think you know about speed. If you are sitting in a car traveling at 60 miles per hour and you throw a baseball forward at 30 miles per hour, simple mathematics tells you that baseball is now traveling at 90 miles per hour relative to someone standing on the sidewalk. This feels obvious. This feels true. This is how Isaac Newton understood the world, and for over 200 years, this understanding served humanity perfectly well. We built trains. We calculated artillery trajectories. We sent cannonballs through the air with predictable precision. Newton's laws were not suggestions. They were commandments carved into the bedrock of physics, describing a universe where velocities simply add together like numbers on a ledger. You could, according to Newton, achieve any speed you wanted. There was no cosmic speed limit. If you had enough force, enough time, enough patience, you could accelerate forever. The universe was infinite in possibility, limited only by practical concerns of fuel and time. But Newton never had access to the right experiments. He never saw what happens when things move really fast. He lived in a world where the fastest things humans could observe were cannonballs and perhaps lightning. He had no way of knowing that the universe conceals its deepest secrets behind a veil of speed that 19th century technology could not pierce. The first crack in this comfortable worldview appeared in 1887 in a basement laboratory in Cleveland, Ohio. Two American physicists, Albert Michelson and Edward Morley, were trying to measure something that everybody assumed must exist: the luminiferous ether. This was the invisible substance that scientists believed filled all of space, the medium through which light waves propagated, just as sound waves propagate through air. Think about what this assumption meant. Sound needs air. Ocean waves need water. Scientists reasoned that light waves must also need something to wave through. This hypothetical substance, the ether, was thought to be perfectly transparent, perfectly stationary, and perfectly ubiquitous. The entire universe was supposedly swimming in it. Their experiment was elegant. As Earth orbited the Sun at roughly 67,000 miles per hour, it should be plowing through this cosmic ether. By measuring the speed of light in different directions, Michelson and Morley expected to detect Earth's motion through this ethereal substance. The light traveling upstream through the ether should move slower relative to Earth than light traveling downstream. The apparatus they built was a masterpiece of precision. They floated their optical equipment on a pool of mercury to isolate it from vibrations. They took measurements over months, accounting for Earth's changing velocity as it orbited the Sun. They were meticulous, rigorous, determined. They found nothing. The speed of light was exactly the same in every direction. No matter how Earth moved, no matter which way they pointed their apparatus, light stubbornly refused to acknowledge that anything was moving at all. The ether wind they expected to detect simply did not exist. This was not a small discrepancy. This was not measurement error. This was the universe saying something fundamental about the nature of reality, and almost nobody understood what it meant. The Michelson-Morley experiment is sometimes called the most important failed experiment in the history of physics, because its failure revealed a truth more profound than its success ever could have. For 18 years, physicists tried to explain away the result. They invented increasingly baroque theories. They suggested that objects physically contract when moving through the ether. They proposed that the ether itself was somehow dragged along by moving objects. Hendrik Lorentz and George Fitzgerald, working independently, developed mathematical transformations to make the numbers work, but these were bandages on a wound that ran far deeper than anyone realized. The transformations Lorentz developed were correct. The mathematics worked perfectly, but Lorentz did not understand why. He believed he was describing real physical contractions caused by motion through the ether. He was solving the wrong problem with the right equations. Then, in 1905, a 26-year-old patent clerk in Switzerland looked at the problem differently. Albert Einstein did not try to save the ether. He killed it. He accepted the experimental result at face value and asked a simple question. What if the speed of light really is constant for all observers? Not because of some trick, not because of some hidden mechanism, but because that is simply how the universe works. The consequences were immediate and terrifying. Einstein published his paper on the electrodynamics of moving bodies on September 26, 1905. The title was deliberately modest, almost boring. The content was revolution. This was one of 4 extraordinary papers Einstein published that year, his so-called miracle year, including papers that would earn him the Nobel Prize and establish the foundation of quantum mechanics. But the Relativity paper was the one that rewrote the rules of reality. If light always travels at the same speed for every observer, Einstein realized, then something else must give. Time itself must bend. Space itself must distort. The familiar architecture of Newtonian physics was not wrong for everyday purposes, but it was incomplete. It was an approximation that broke down the moment speeds became significant compared to the speed of light. Einstein wrote in that paper words that still echo through physics. Thus, when V equals c, W becomes infinite. Velocities greater than that of light have, as in our previous results, no possibility of existence. There it was, in black and white. Not a suggestion, not a preliminary finding, a statement of impossibility backed by the full force of mathematical logic. Here is the terrifying implication. Go back to your car and your baseball. You throw the baseball forward at 30 miles per hour. To someone on the sidewalk, it should be traveling at 90 miles per hour. And at these everyday speeds, it is. The difference is so small that no measurement could detect it. But what if you were traveling at half the speed of light, about 335 million miles per hour, and you turned on a flashlight? Newtonian physics would say that light should now be traveling at 1.5 times the normal speed of light, but it does not. The light still travels at exactly 299,792,458 meters per second, always, forever, regardless of how fast you are moving when you turn on that flashlight. This seems impossible. It seems to violate basic logic. If you are moving at half light speed and you shine a light forward, surely the light should appear to move away from you at half the speed it normally would. But it does not. It still moves away from you at full light speed. The mathematics of special relativity describes exactly how this works. It involves something called the Lorentz factor, represented by the Greek letter gamma. This factor starts at 1 when you are stationary, and it grows as you accelerate. At 10% the speed of light, gamma is only about 1.05, barely noticeable. At 50%, gamma has grown to about 1.15, still manageable. But watch what happens as you push higher. At 90% the speed of light, gamma reaches 2.29. At 99%, it jumps to 7.09. At 99.9%, it explodes to 22.4. And at 99.99%, the number that gives this documentary its title, gamma reaches 70.7. This is not a linear progression. This is exponential growth that becomes vertical as you approach the speed of light. The Lorentz factor approaches infinity as velocity approaches the speed of light. And infinity, in physics, is another word for impossible. Let me show you what this means in practice. The Large Hadron Collider, operated by CERN on the border of France and Switzerland, is the largest and most powerful particle accelerator ever built. It is a ring 27 kilometers in circumference, buried up to 175 meters beneath the countryside. Over 10,000 scientists from more than 100 countries contributed to its construction, which took over a decade and cost approximately $10 billion. Inside this machine, superconducting magnets cooled to temperatures of negative 271.3 degrees Celsius, colder than outer space, guide beams of protons around the ring. The magnets must be this cold to achieve superconductivity, the state in which electrical resistance drops to zero and current can flow without loss. The refrigeration system that maintains these temperatures would qualify as the world's largest refrigerator by itself. The system consumes about 1.3 terawatt-hours of electricity annually, enough to power 300,000 homes for a year. During peak operation from May to December, CERN draws about 200 megawatts, roughly a third of what the nearby city of Geneva uses. Inside this machine, protons are accelerated to energies of 6.5 trillion electron volts per beam. These tiny particles, each with a mass of only about 1.7 times 10 to the negative 27 kilograms, are pushed to velocities of 99.99991% the speed of light. They circle the ring 11,245 times per second, completing each lap in about 89 microseconds. Think about that number for a moment. These protons are traveling at 99.9999991% of light speed. They are missing only 9/10 millionths of a percent. They are so close to the cosmic speed limit that the remaining gap seems negligible, almost a rounding error. But here is what the LHC cannot do. It cannot close that gap. No matter how much more energy scientists pump into those protons, they will never reach exactly the speed of light. The energy required does not scale linearly. It does not even scale polynomially. It scales asymptotically, meaning the curve goes vertical. The LHC's predecessor at the same site was a machine called LEP, the Large Electron Positron Collider. It accelerated electrons to energies of 209 billion electron volts before being dismantled to make way for the LHC. The LHC accelerates protons to 6.5 trillion electron volts, over 30 times more energy. And yet the speed difference between LEP's electrons and LHC's protons is minuscule. At 99.99991%, the speed of light, a proton has a gamma factor of approximately 7,500. Its relativistic energy is 7,500 times greater than its rest mass energy. The proton behaves as if it has the inertia of 7,500 protons at rest. To push it even slightly faster would require exponentially more energy. To reach the actual speed of light would require infinite energy. This is not a technological limitation. This is not a problem we can engineer our way around. This is a fundamental property of the universe, as fundamental as the fact that you cannot divide by zero. The protons at the LHC travel around the ring roughly 400 million times before being discarded or collided. Each circuit, they receive a small boost from radio frequency cavities. Each boost adds energy, but each boost adds less and less speed. The closer the protons get to light speed, the more their added energy goes into increasing their effective mass rather than their velocity. But why? What is actually happening as a particle approaches light speed? What mechanism does the universe employ to enforce this limit? The answer lies in how energy, momentum, and mass relate to each other in relativity. In Newton's physics, kinetic energy scaled with the square of velocity. Double your speed, and you have 4 times the kinetic energy. This made acceleration predictable. It meant there was nothing, in principle, stopping you from going faster and faster indefinitely. Einstein's physics changed this relationship fundamentally. The equation for relativistic kinetic energy is not the familiar 1/2 times mass times velocity squared. Instead, it is the difference between total energy and rest mass energy. And total energy is rest mass energy multiplied by gamma. In mathematical form, kinetic energy equals gamma minus 1 times the rest mass times the speed of light squared. As gamma grows toward infinity, so does the energy required for each incremental increase in speed. At low velocities, this effect is negligible. When the gamma factor is close to 1, classical and relativistic kinetic energies are nearly identical. The difference might be a few parts per million, undetectable by any ordinary measurement. But as you push toward light speed, the relativistic correction becomes dominant, then overwhelming, then absolute. The curve of energy versus velocity, which starts out looking like a gentle parabola, bends upward and eventually becomes vertical. Consider a concrete example. An electron at rest has a rest mass energy of about 0.511 MeV, where MeV stands for million electron volts. This is a tiny amount of energy by everyday standards, but it is a useful unit for particle physics. If you accelerate this electron to 99% the speed of light, its total energy rises to about 3.6 MeV. The kinetic energy alone is about 3.1 MeV, roughly 6 times its rest mass energy. You have put in 6 times the electron's rest energy just to get it to 99% of light speed. But if you push the same electron to 99.9% the speed of light, its total energy rises to about 11.4 MeV. That is more than triple the energy for just 1 additional 9 after the decimal point. To 99.99%, the energy reaches about 36 MeV, another factor of 3 for another 9. Each additional digit of precision costs you roughly 3-fold more energy than the previous digit. Now extrapolate. to reach 99.9999% would require about 114 MeV. To reach 99.9999%, about 360 MeV. The pattern continues relentlessly. To reach exactly light speed would require energy that is not just large, not just astronomical, but literally infinite. No amount of fuel, no configuration of power sources, no technological advancement can provide infinite energy. It is not that we have not figured out how. It is that infinite is not a number you can reach. We have experimental proof of these effects dating back over a century. The confirmation came not from one decisive experiment, but from a converging body of evidence that grew more precise with each decade. In 1901, a German physicist named Walter Kaufmann began a series of experiments that would ultimately confirm what Einstein later predicted. Kaufmann was studying beta rays, which are high-speed electrons emitted by radioactive materials. These were strange particles at the time. Scientists were still debating whether electrons were fundamental or composite, whether they were waves or particles, whether their properties remained constant or changed with circumstances. Unlike the electrons in cathode ray tubes, which moved at relatively modest speeds of perhaps 30% of light speed, beta particles from radium traveled at velocities approaching 90% the speed of light. This made them ideal for testing how motion affects physical properties. Kaufmann measured how these fast-moving electrons were deflected by electric and magnetic fields. He passed the electrons through parallel electric and magnetic fields, causing them to curve in two perpendicular directions. By photographing the resulting curves, he could determine both the velocity and the charge-to-mass ratio of the electrons. What he found was striking. The electrons' response to the fields changed as their velocity increased. It was as if they were becoming harder to accelerate, as if their inertia was increasing with speed. Electrons moving at 90% of light speed behaved as if they were significantly more massive than electrons moving slowly. At the time, Kaufmann interpreted this through older theories, including one developed by Max Abraham that treated electrons as rigid spheres of distributed charge. But after Einstein published his special relativity paper, physicists realized that Kaufmann's data could be explained by the Lorentz-Einstein equations. The experiments were repeated and refined over the following decades. Alfred Bucherer in 1908 conducted more precise measurements using a velocity filter technique. Günther Neumann in 1914 added further refinements. Each generation of experiments used better equipment, more careful controls, and more sophisticated analysis. By the 1940s, particle accelerators had become accurate enough to confirm the relativistic formulas beyond any reasonable doubt. A critical 1938 analysis by C.T. Zahn and A.H. Spies showed that earlier experiments, while pointing in the right direction, had been too imprecise to definitively distinguish between competing theories. But modern accelerators left no room for doubt. Today, these effects are not theoretical curiosities. They are engineering constraints that particle physicists deal with every day. Every particle accelerator in the world, from small medical cyclotrons used for cancer treatment to the massive LHC, must account for relativistic effects in their design. The magnets that steer particle beams, the radio frequency cavities that boost their energy, the timing systems that control beam injection. All of these must be calibrated for particles whose effective inertia increases dramatically as they approach light speed. The engineers who design these machines do not debate whether relativity is correct. They cannot afford to. A synchrotron that ignored relativistic effects would send its particle beams crashing into the walls within microseconds. The equations of special relativity are built into the fundamental design parameters of every high-energy physics facility on Earth. Perhaps you are thinking, surely the effects we experience in everyday life could not be so constrained. We launch spacecraft. We dream of interstellar travel. Humanity has built machines that move faster than anything our ancestors could have imagined. The Parker Solar Probe, launched in 2018, reached speeds of 430,000 miles per hour during its close passes around the Sun in 2024, becoming the fastest object ever built by humanity. This is a genuine achievement, a marvel of engineering that required solving problems of heat shielding, orbital mechanics, and power generation that would have seemed impossible a generation ago. But let us put that number in perspective. The speed of light is approximately 670,699 miles per hour. The Parker Solar Probe's record-breaking velocity of 430,000 miles per hour is roughly 0.064% of the speed of light, not 64%, 0.064%. We have built the fastest machine in human history, and it would take over 1,500 Parker Solar Probes traveling end-to-end to match the speed of a single photon. Voyager 1, the most distant human-made object, launched in 1977 and now more than 15 billion miles from Earth, travels at about 38,000 miles per hour. That is approximately 0.006% of light speed. At that rate, it will take Voyager 1 over 70,000 years to reach the nearest star system, Proxima Centauri. The gap between our fastest achievements and even modest fractions of light speed is staggering. And that gap is not primarily a result of insufficient technology. It is a result of energy requirements that scale in ways our intuition cannot grasp. Consider what it would take to accelerate a spacecraft to just 1% of the speed of light, roughly 6.7 million miles per hour. A spacecraft massing 10,000 kilograms, about the size of the Space Shuttle orbiter, would require approximately 4.5 times 10 to the 17th joules of kinetic energy. How much energy is that? It is about 125 billion kilowatt hours. The entire United States generates about 4 trillion kilowatt hours of electricity per year. So accelerating one small spacecraft to 1% of light speed would require about 3% of America's annual electrical output delivered to a single object. And that is just 1%. To reach 10% would require roughly 100 times more energy, about 3 years of total American electrical generation. To reach 90% would require thousands of times more than that. To reach 99.99% would require energy supplies that exceed anything humanity has ever produced by many orders of magnitude. The rocket equation makes things even worse. To accelerate a spacecraft, you must carry fuel, but fuel has mass. To accelerate that fuel, you need more fuel. The equation describing this relationship is exponential, and when you combine it with relativistic effects, the results become absurd. Using the most efficient theoretical propulsion system, matter-antimatter annihilation, converting 100% of mass into thrust energy, you would need approximately 57 kilograms of fuel for every kilogram of payload just to reach a nearby star at relativistic speeds without stopping. If you want to slow down at your destination, that ratio jumps to 886 to 1. If you wanted to reach the Andromeda Galaxy, 2 million light-years away, and stop there, you would need over 4 billion tons of fuel for every kilogram of spacecraft. The fuel would outmass the payload by a factor of 4 trillion. These numbers are not technological barriers waiting to be overcome by better engineering. They are mathematical consequences of the laws of physics, as unavoidable as the impossibility of finding the largest prime number. Let us now address something deeper. The mathematics tells us that infinite energy would be required to reach light speed. But what does the physics actually say is happening? What is the universe doing when it refuses to let matter reach this velocity? There are several ways to understand this, and each reveals something profound about the nature of reality. The first perspective focuses on inertia. In classical physics, inertia is a measure of how much an object resists acceleration. It is directly tied to mass. A more massive object requires more force to achieve the same acceleration, and the relationship is linear. Double the force, double the acceleration, assuming mass stays constant. In relativistic physics, inertia is not constant. As an object moves faster, its resistance to further acceleration increases. This is sometimes described as an increase in relativistic mass, though modern physicists prefer to say that mass remains constant while the relationship between force and acceleration changes. The distinction is partly semantic, but it matters for avoiding conceptual errors. Either way, the practical effect is the same. The faster something moves, the harder it becomes to make it move faster still. At speeds close to light, this effect dominates all others. A proton traveling at 99.9999991% light speed at CERN requires the same force to accelerate by 1 meter per second squared as a stationary proton weighing 7,500 times more would require. The universe responds to your attempt to accelerate it as if you were trying to push something immensely heavier than it appears. Particle physicists observe this every day. When beams are accelerated in synchrotrons, the magnetic fields that keep them on course must be continuously adjusted as the particles gain energy. The fields must grow stronger and stronger to bend the paths of particles that are becoming harder and harder to deflect. This is not a design inconvenience. It is the universe enforcing its laws in real time. The second perspective focuses on time. Special relativity tells us that time itself passes differently for objects in motion relative to stationary observers. The faster something moves, the slower its clock ticks from an outside perspective. This is called time dilation, and it has been confirmed countless times experimentally. Consider the muon, an unstable particle created when cosmic rays strike Earth's atmosphere. Muons are similar to electrons, but about 200 times more massive. They are created about 15 kilometers above sea level when high-energy protons from space collide with atmospheric molecules. Muons have a half-life of about 2.2 microseconds. At the speeds they travel, roughly 99.5% of light speed, they should decay long before reaching Earth's surface. Classically, they would travel only about 660 meters before half of them decay. Yet we detect abundant muons at sea level, tens of kilometers from where they were created. The explanation is time dilation. From Earth's perspective, the muons' internal clocks run slow. Their 2.2 microsecond half-life stretches to about 22 microseconds, giving them time to reach the surface. The experiment was famously conducted by David Frisch and James Smith in 1963. They measured moon counts at the top of Mount Washington in New Hampshire at an altitude of about 1,900 meters and compared them to counts at sea level in Cambridge, Massachusetts. Classically, they should have detected only about 27 moons at sea level for every 563 measured on the mountain. Instead, they detected about 412, a ratio that matched the predictions of special relativity with remarkable precision. This experiment has since been repeated by undergraduate physics students around the world, using increasingly sophisticated equipment. The results are always the same. Moons live longer when moving fast, exactly as relativity predicts. But here is the deeper implication. As an object approaches the speed of light, time dilation becomes extreme. At 99.99% light speed, time passes 70 times slower for the moving object than for a stationary observer. At 99.999%, time slows by a factor of over 700. At exactly light speed, the math says, time stops entirely. This is not a meaningful physical state. An object experiencing no passage of time cannot undergo any physical processes. It cannot change, evolve, or interact. It is frozen at the boundary of causality. And this reveals something fundamental. The speed of light is not just a limit on how fast things can move. It is a limit on how physics itself can operate. The third perspective is perhaps the most profound. It concerns the relationship between energy and mass. Einstein's famous equation, E equals mc squared, tells us that energy and mass are interchangeable. This is not a metaphor. It is literal. When you add energy to a system, you add mass. When you extract energy, you reduce mass. The conversion factor is the speed of light squared, an enormous number that explains why tiny amounts of mass contain staggering amounts of energy. This relationship powers nuclear reactors. When uranium atoms split, the fragments have slightly less total mass than the original atom. That missing mass has become energy, about 200 million electron volts per fission. The sun converts about 4 million tons of mass into energy every second through nuclear fusion, and has been doing so for 5 billion years. When you accelerate an object, you are adding kinetic energy to it. That energy has to go somewhere. In relativistic physics, the added energy increases the object's total energy content. And that means, in a very real sense, that the object becomes more massive, not larger, not denser in the sense of being more tightly packed, but possessing more gravitational and inertial mass. As you approach light speed, more and more of your propulsion energy goes into increasing the object's mass rather than its velocity. The closer you get to light speed, the worse this ratio becomes. Near light speed, almost all the energy you add becomes mass, and almost none becomes velocity. This is why the required energy becomes infinite. You are trying to fill a container that grows larger as you fill it. You are racing toward a finish line that recedes as you approach. The structure of space-time itself conspires to prevent any massive object from reaching the speed of light. There is yet another way to understand this barrier, and it involves the geometry of space-time itself. In special relativity, space and time are not separate entities. They are woven together into a four-dimensional fabric called space-time. Objects trace paths through this fabric, paths called world lines. And the geometry of space-time, unlike the flat geometry of Euclidean space, is what mathematicians call hyperbolic. In space-time geometry, there are three classes of intervals between events: time-like, space-like, and light-like. Objects with mass can only travel along time-like paths. Their world lines must always point predominantly toward the future, never parallel to spatial directions. Light travels along light-like paths, which form the boundaries between time-like and space-like regions. The speed of light is not just a speed in this framework. It is a geometric boundary. It is the edge of the light cone, the surface that divides what an object can possibly reach from what is forever inaccessible. Crossing that boundary is not like exceeding a speed limit on a highway. It is like trying to travel north from the North Pole. The direction simply does not exist. This geometric understanding explains why the speed of light appears in so many physical equations beyond those describing motion. It appears in the relationship between electric and magnetic fields. It appears in the equations of gravity in general relativity. It appears in quantum mechanics. It appears as a fundamental constant because it is not merely a property of light. It is a property of space-time itself. Light travels at this speed not because it is special, but because it is massless. Having no mass, light must travel along light-like paths exactly at the geometric boundary. Anything with mass, no matter how small, is confined to time-like paths, forever inside the light cone, forever short of the boundary. You might wonder, if the universe enforces this limit so absolutely, are there any loopholes? Can we cheat? Can we find exceptions? There are apparent exceptions that turn out not to be exceptions at all. In certain media, light travels slower than its vacuum speed. In water, light moves at about 75% of its vacuum speed. In glass, it slows even more. In specialized laboratory conditions using ultra-cold atoms of sodium, light has been slowed to walking pace, just a few meters per second. Does this mean objects can exceed the local speed of light? Yes, they can, and they do. When high-energy particles from nuclear reactors or cosmic rays enter water, they can travel faster than light does in that medium. This produces Cherenkov radiation, a beautiful blue glow caused by the optical equivalent of a sonic boom. The particles are exceeding the local speed of light, but they are not exceeding the speed of light in vacuum. The underlying limit remains intact. You can see Cherenkov radiation in photographs of nuclear reactor pools. That eerie blue glow surrounding the reactor core is not a science fiction effect. It is real physics, caused by electrons exceeding the local speed of light in water. Another apparent loophole involves the expansion of the universe. Galaxies billions of light years away are receding from us at speeds that exceed the speed of light. This is not a violation of special relativity because the galaxies are not moving through space faster than light. Space itself is expanding, carrying the galaxies along with it. The speed limit applies to motion through space-time, not to the behavior of space-time itself. There are also hypothetical particles called tachyons that would, if they existed, travel always faster than light. They would require imaginary mass in the equations, a mathematical concept that has no clear physical meaning. Their existence would create severe problems for causality, potentially allowing effects to precede causes. Despite decades of searching, no tachyon has ever been detected. Most physicists believe they are mathematical curiosities, not physical realities. What about warp drives and wormholes, the staples of science fiction? These concepts do not violate special relativity in the technical sense. They instead invoke general relativity, Einstein's theory of gravity, which allows space-time itself to curve and distort in ways that could, theoretically, provide shortcuts, but general relativity also imposes constraints. Building a warp drive would require exotic matter with negative energy density, something that may not exist in any form capable of being engineered. And the energy requirements for such distortions are typically estimated in multiples of the Sun's mass, converted entirely into warping spacetime. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical way to move faster than light by contracting space in front of a spacecraft and expanding it behind. But creating such a bubble would require energy equivalent to the mass of Jupiter, converted entirely into exotic matter. Later refinements reduced this estimate, but never to anything remotely practical. The loopholes, on close examination, are either not loopholes at all, or require conditions so extreme that they offer no practical path around the fundamental limit. Let us talk about what happens to the universe itself as you approach light speed, because the effects are not limited to requiring more energy. Reality itself begins to distort in ways that seem impossible. Length contraction is the twin of time dilation. As an object moves faster, its length in the direction of motion decreases from the perspective of a stationary observer. At 99% of light speed, an object appears about 14% of its rest length. At 99.99%, it appears only 1.4% of its rest length. At exactly light speed, the math says it would have zero length in the direction of motion. This is not an optical illusion. This is not the object compressing itself. This is space itself behaving differently for different observers. A rocket ship 50 meters long, traveling at 99.99% of light speed, would appear to a stationary observer to be less than a meter from nose to tail. For the astronauts inside, nothing would seem unusual. Their rulers would measure the ship at 50 meters. Their clocks would tick at normal rates. But when they looked out at the universe, they would see something strange. The distance to their destination would appear contracted. A star 20 light years away would appear to be only about 0.3 light years distant. This explains how interstellar travel could theoretically be accomplished within a human lifetime, even without faster than light travel. An astronaut accelerating at 1g, the comfortable acceleration we feel from Earth's gravity, would reach 99.99% of light speed in about 4.5 years of ship time. From Earth's perspective, about 70 years would have passed. But from the astronaut's perspective, the distance to any destination would be contracted by a factor of 70. The entire galaxy, 100,000 light years across, could be traversed in about 12 years of ship time. But when the astronaut arrived, 116,000 years would have passed on Earth. Everyone they knew would be dead. Their civilization might have risen and fallen multiple times. This is the twin paradox in action, and it reveals the cost of relativistic travel. You can get anywhere in your own lifetime, but you can never go home. We should address one more phenomenon before concluding: the relativistic Doppler effect. When an ambulance passes you, its siren shifts in pitch. Approaching, the sound is higher. Receding, it is lower. This is the classical Doppler effect, caused by the motion of the source relative to the observer. Light experiences a similar effect, but relativistic corrections make it more extreme. An object approaching you at relativistic speeds would appear shifted toward the blue end of the spectrum. An object receding would appear shifted toward the red. At extreme speeds, visible light could shift into ultraviolet or infrared, becoming invisible to human eyes. At 99% of light speed, the shift factor is enormous. Light that starts as green would shift to gamma rays if the source is approaching, or to radio waves if it is receding. The universe would look completely different to a relativistic traveler with stars ahead compressed into a bright forward cone and stars behind stretched into dim redness. This has practical implications. The cosmic microwave background radiation left over from the Big Bang permeates all of space at a temperature of about 2.7 Kelvin. It is harmless at everyday speeds. But for a spacecraft traveling at relativistic velocities, this background radiation would be Doppler shifted into dangerous, high-energy photons. After a few years of acceleration at 1g, the cosmic background would be shifted into lethal X-rays. The ship would need shielding that does not yet exist. The universe itself becomes hostile to relativistic travel, presenting yet another barrier beyond the energy requirements. Let us return to the question posed at the beginning. Why can you not reach 99.99% the speed of light? The answer, in its starkest form, is that you can, in principle, but doing so requires energy expenditures that scale beyond comprehension as you approach that figure. And each additional 9 after the decimal point, each increment toward perfection, requires exponentially more than the last. At 99% the speed of light, the Lorentz factor is 7.09. At 99.9%, it jumps to 22.4. At 99.99%, it reaches 70.7. At 99.999%, it becomes 223.6. At 99.999%, it exceeds 700. The pattern is relentless. Each factor of 10 closer to light speed multiplies the energy requirement by another factor of approximately 3. To accelerate a single proton to 99.999% light speed, you need roughly 70 times its rest mass energy. To accelerate something as massive as a spacecraft would require energy stores that dwarf the output of stars. But the real insight is not about the numbers. It is about what the numbers reveal. The speed of light is not arbitrary. It is not a limit that a more advanced civilization could overcome with better technology. It is woven into the fabric of reality at the deepest level. It appears not because light is special, but because space-time has a structure that distinguishes between what can be reached and what cannot. When Einstein derived his equations, he started from two simple postulates: that the laws of physics are the same in all inertial frames, and that the speed of light is the same for all observers. Everything else followed: time dilation, length contraction, the equivalence of mass and energy, the impossibility of reaching light speed. All of it emerges from those two assumptions, and both assumptions have been verified by every experiment ever conducted. The universe is not hiding a secret shortcut. The mathematics is not concealing an exception. The limit is real, it is absolute, and it is fundamental. And yet, there is a strange beauty in this limitation. Consider what it means for the passengers on a hypothetical spacecraft accelerating toward a distant star. As their speed increases, time dilation stretches their seconds into minutes for those they left behind. Length contraction shrinks the apparent distance to their destination. At 99.999% light speed, a journey of 100 light years would feel like only about a year and a half to the travelers, even as a century passed on Earth. The cosmic speed limit does not prevent interstellar travel, it transforms it. The travelers could, in principle, cross the visible universe in a single human lifetime, experiencing only decades while billions of years pass for the rest of existence. they would arrive in a future unimaginably distant from their departure, strangers to everything they once knew. The speed of light is not just a barrier. It is a gatekeeper between different experiences of time itself. It divides the universe into what you can reach and what will forever be beyond your horizon. It imposes a cost on motion that becomes absolute at the limit. Every GPS satellite in orbit must account for relativistic effects. The satellites move fast enough, about 14,000 kilometers per hour, that their clocks tick about 7 microseconds per day slower than clocks on Earth due to their velocity. They also tick faster by about 45 microseconds per day due to being higher in Earth's gravitational field, an effect from general relativity. Without corrections for both effects, GPS would accumulate errors of about 10 kilometers per day. You use relativity every time you check your location on your phone. The cosmic speed limit is not some abstract curiosity of theoretical physics. It is built into the infrastructure of modern civilization. In the end, the question of why you cannot reach 999.999% the speed of light has a profound answer. You can approach it. The particles at CERN approach even closer. But the universe extracts a price for every increment, and that price grows without limit. Approaching the speed of light asymptotically approaches, requiring all the energy in existence. And the speed of light itself? That is not a speed in the usual sense. It is the speed at which causality itself propagates. It is the conversion factor between space and time. It is the boundary between the possible and the impossible, written into the equations of reality since the beginning of time. You cannot reach it because it is not a destination. It is the shape of the universe itself. Look at your hand again. It is still there, still trembling slightly with the heartbeat that keeps you alive. When you move it through space, when you walk across a room, when you drive down a highway, you are negotiating with space-time. At your everyday speeds, the negotiation is trivial, the terms are favorable, and the universe barely notices. But behind that trivial transaction lies the same mathematics that governs protons at CERN, muons falling through the atmosphere, and the light streaming from distant galaxies. The same equations that describe your hand's gentle motion also describe the absolute barrier that no massive object can ever cross. You are moving through a universe that has rules. Those rules are not suggestions. They are the architecture of existence. And one of those rules, perhaps the most fundamental of all, is that there is a speed beyond which nothing with mass can ever travel. Not because we lack the technology, not because we have not tried hard enough, but because that is how space-time works. That is what it means to have mass in a relativistic universe. The speed of light is not a wall you hit. It is a limit you can never reach. And in that mathematical impossibility lies one of the deepest truths about the cosmos we inhabit. Some things are not forbidden. They are simply impossible. And the distinction between those two words contains all the majesty and terror of modern physics. The hand you are looking at will never travel at the speed of light. Neither will you. Neither will anything that has mass, from the smallest particle to the largest star. But perhaps that is fitting. Perhaps the universe needs limits. Perhaps infinity, that concept we chase in mathematics and philosophy, is meant to remain forever out of reach, because a universe without limits, a universe where anything could travel at any speed, would be a universe where cause and effect became meaningless, where time lost its arrow, where existence itself became incoherent. The speed of light is not a prison wall. It is the edge of a sandbox, beyond which the game of physics ceases to make sense. We can approach that edge. We can study it. We can send particles to within billionths of a percent of it, but we cannot cross it. And in that limitation, strangely, lies a kind of freedom, because the universe we inhabit, constrained though it is comprehensible. It follows rules we can discover. It obeys equations we can write. It rewards our curiosity with understanding. The speed of light is the universe's way of saying this far and no farther. But within these bounds, an entire cosmos awaits exploration.